let's talk about conservation of momentum real quick. So, you got a little bit of an exposure to this in the online simulation you did a few days ago, but now we're going to actually put some math on top of it and define everything that you talked about. So, the baseline definition of conservation of momentum is that for objects in an isolated system, momentum is conserved during collisions. All right, so let's talk about some things that we said in here. An isolated system simply means that no external forces are acting on the system. Everything is inside of the system. There's no outside forces. And that could be friction, that could be air resistance. There's nothing that's going to be, in a way, taking momentum away. All right? Conservation simply means when the total amount of something does not change. All right? We see conservation laws all over the sciences. This is just another one saying that the momentum at the beginning, so that's P initial, is equal to the momentum at the end. So the overall change of momentum is 0. And that's what you guys saw approximately in that simulation. All right. Now let's be clear here. P initial is the total momentum of the system. Everything in that system before the collision. P final is the total momentum of the entire system after the collision. All right. So talking about how we would problem solve with something like this, it's very important, and I know I've said this pretty much in every unit we've done, but it's super important that you draw a picture before and after the collision. We have to keep track of all of these variables. Within that, you need to identify your unknowns as well, okay? From there, you need to identify your system. Is everything involved in the system? Are there some things outside of the system? What is it? Then you're going to write a conservation of momentum equation. We're going to talk more about how to do this, but it always starts with this step right here. Initial momentum is equal to the final momentum. Finally, you're going to rearrange and solve for your unknown variable, and then you're going to solve the equation. All right? So let's talk a little more about setting up this conservation of momentum equation. So again, it always starts with P initial is equal to P final. Now, what you want to do is you want to look at your picture that you've drawn for before and after and determine how many objects you have before the collision and after the collision. So if that's tough for you to understand, let's look at an example. Let's say that there's a pool ball that collides with another pool ball, and when they hit, they bounce off into separate directions. So in this scenario, all you have here is you have one ball moving towards another ball, and then after the collision you still have the two separate pool balls, and they're just moving in opposite directions. All right, two objects at the beginning, two objects at the end. So if we wanted to look at what this equation is going to look like, well, we start with P initial is equal to P final. Now P initial, remember, refers to the total initial momentum. So when we're writing the initial momentum, we need to say the initial momentum of pool ball number 1 plus the initial momentum of pool ball number 2 is equal to the final momentum of pool ball 1 plus the final momentum of pool ball 2. Two objects at the beginning, two objects at the end. All right. So let's look at some examples. Types of collisions. You got a bit of exposure to this in the simulation. We're going to define them now. An elastic collision is where two objects collide and bounce off of each other. They do not stick together. In this situation, momentum is conserved and kinetic energy is conserved. That's going to be important. Both of these things are conserved when objects bounce off of each other. All right? Purely, perfectly elastic collisions rarely exist in the real world because when two things collide, they're going to stick together for an infinitely small amount of time. Inelastic collisions are when two objects collide and stick together. It says stick off of each other. It's supposed to say stick together. My bad. Now, in this situation, momentum is still conserved, just like in an elastic collision. However, kinetic energy is not conserved. Now, I want you to try and think about why that might be, all right? Kinetic energy is not going to be conserved here simply because you're losing energy to heat, right? You've got these two things colliding, and when they collide, and we haven't really talked about kinetic energy, but kinetic energy is just the energy of motion, All right. Now, if kinetic energy can't be conserved, it must be going somewhere. And in this case, it's going into heat energy. All right. Now, explosions are also included in this type of collision because in this situation, you have objects that start together as one thing and then they move apart after something causes them to explode apart from each other. So let's look at this. We've got a 2 kilogram ball moving at 3 meters per second collides with a 3 kilogram ball at rest. The 2 kilogram ball moves at negative 0.6 meters per second after the collision. What is the velocity of the 3 kilogram ball? And what type of collision is this? All right, so we go back. Oh boy. Step number 1, whatever these were. Here we go. Step number 1, draw a picture before and after the collision. Okay, so before and after the collision. Let's go ahead and do that. So we got before. Here's our 2 kilogram ball. So we'll say mass 1 is 2 kilograms. V1 initial is 3 meters per second. All right, and it's moving in the positive direction. And we got ball 2 here. And ball 2 has a mass of 3 kilograms and a V initial of 0 meters per second. Now, after the collision, it says that the 2 kilogram ball moves at negative 0.6 meters per second. All right, so here's the 2 kilogram ball. V final of 1 is negative 0.6, and it's moving to the left now because it's negative. And ball 2 is going to have some velocity now, but we don't know what the final velocity of ball 2 is. That's what we're trying to solve for. All right. So we need to identify our unknown. Here's our unknown right here. This is what we're solving for. All right. Now we need to set up a conservation equation. And let's talk about our system. Our system here is going to be the 2 balls. All right. So let's set up a conservation equation. In our conservation equation, we start with P initial is equal to P final. All right. Now, let's talk about things that have momentum. At the beginning, I have 2 objects. So I have the initial momentum of object 1 plus the initial momentum of object 2 equals the final momentum of 1 plus the final momentum of 2. All right? Now, we know from a few days ago that momentum is equal to mass times velocity. So let's substitute that in. Initial momentum of 1 is m1 times v1 initial plus m2 times v2 initial is equal to m1 times v1 final plus m2 times v2 final. All right? This is where we can actually start to do things. Now, all I've done here is I've replaced these P initials and P finals with the equation for momentum. All right? Now, let's look at this. I know what M1 is. I know what V1 initial is. I know what M2 is. I know what V2 initial is. I know what V1 final is. I only don't know what this is right here. So I need to rearrange this. All right. Now here's how we're going to do this. Oh no. To go away. Oh, that's devastating. All right. Sorry, guys. So we had M1, V1 final. M1, V1 final plus M2, V2 initial. Sorry, this was initial. Is equal to M1, V1 final plus M2, V2 final. Sorry about that, guys. That's what we're isolating. So let's rearrange this and solve. I'm going to take this to the other side. All right, so I have M1, V1 initial plus M2, V2 initial minus M1, V1 final is equal to M2 times V2 final. All right, now I need to divide by M2. And now I can actually plug in my variables. So M1 was 2 kilograms. V1 initial is 3 meters per second. M2 is 3 kilograms. V2 initial is 0 meters per second. M1 was 2 kilograms. V1 final was negative 0.6 meters per second. And M2 is 3 kilograms is equal to V2 final. All right. So we got 2 times 3 is 6. 6 plus 0 minus 2 times 0.6. And then we divide that by 3. And what we get is that V2 final is 2.4 meters per second. And notice that this is a positive number. And that positive should make sense here because we would expect these objects to move in opposite directions after the collision. All right. And what type of collision is this? Well, I have 2 objects at the beginning, 2 objects at the end. Therefore, this must be an elastic collision. Elastic. Because the objects bounce apart. All right, last example. We've got a 125 kilogram boat moving at 12 meters per second. A 65 kilogram person suddenly jumps into the boat. What is the velocity of the boat and the person after the collision? All right, let's draw a picture. So before, we got a boat. Here's the boat. The mass of the boat, let's say mass 1, is 125 kilograms. And it is moving along. V1 initial of 12 meters per second. After the collision, we still have the boat. Now this boat has a person in it. All right, so we have mass 1 of the boat is 125. But now the mass of the person, M2, is 65 kilograms. All right, and we want to know what is V1 final. So here's what we're solving for. My system is the boat and the person, so let's set up an equation. P initial is equal to P final. All right. Now let's think about this. I have 1 object at the beginning, so that's P1 initial. And at the end I have 2 objects, so that's P2 initial, P1 final plus P2 final. Now what are my 2 objects at the end? Well, they're the boat and the person. And they're combined. So let's see how we're going to work with this. So P1 initial is M1 times V1 initial. Now, P1 final and P2 final. Well, let's think about this. Those things are together. So I have M1 V1 final plus M2 V2 final. Let's think about this. If the boat and the person are moving together, then that means that V1 final is equal to V2 final. Now, if V1 final is equal to V2 final, then here's how I can rearrange this. I can write this as M1 plus M2 times V final, because I'm just going to end up calling this V final. And this should make sense. If you look at this, this is saying that the total mass of the boat and the person times the velocity is equal to the momentum of the boat and the person combined. All right? Now let's think about what we're solving for here. We're solving for what is V final. I know what M1 is, I know what V1 initial is, and I know what M2 is. So let's rearrange and solve. In order for me to do this, to get V final by itself, I need to divide by the quantity M1 plus M2. And then I can plug in. All right, so here's what I get. M1 is 125 kilograms. Velocity was 12 meters per second. Divided by 125 plus 65 is equal to V final. So I get 125 times 12 divided by 125 plus 65. And I get 7.9 meters per second. Now again, conceptually this should make sense. I'm moving slower than I was at the beginning, but I'm still moving in the positive direction. What type of collision is this? Well, I have 1 object at the beginning, or I have 2 separate things at the beginning and 1 thing combined at the end. So this would be inelastic because 2 things are sticking together. All right. Thanks, guys. Have a great day. Let me know if you have questions.